Good day everyone. Today we're diving into the critical topic of transmission line protection. When we talk about electricity, reliability is paramount, and these protection systems are the unsung heroes that keep our grid running safely and reliably even when things go wrong. The goal of this presentation is to explain the fundamental concept from why we need protection in the first place to the advanced techniques we use to achieve milliseconds level isolation of faults. So for the first slide, the need for speed. The moment a fault occurs, a lightning strike, a tree branch hitting a line, we enter a race against time. The primary law of protection is threefold and speed key to all of them. So first is fault isolation. The entire goal is to isolate that tiny section of the line where the fault is located. We're talking about the operating in cycles, typically less than 100 milliseconds. If the fault is allowed to burn for too long, it can permanently damage high voltage conductors or even cause a tower to collapse. Next is system stability. This is perhaps the most critical technical reason. A severe fault, especially one involving all three phases, acts like a huge drag on the entire electrical system. It causes severe voltage sags and current surges. If the fault isn't cleared instantly, generators across the system can lose synchronism, leading to cascading outage and widespread blackouts. Fast clearing won't maintain grid stability. So lastly is safety. Finally and most obviously, we must de-energize equipment to protect personnel and public from hazardous voltage. Next slide, types of faults. What exactly are we protecting against? The table breaks down the typical fault types. The key takeaway here is the statistics. So, while the three-phase fault is the most severe and symmetrically short circuit with the highest possible current, it is also the rarest, occurring about 5% of the time. The vast majority of issues, approximately 80%, are single line to ground, SLG faults. This is usually environmental and insulator flushing over due to moisture, a lightning strike, or a wire contacting the ground. Because SLG faults are so common, the design of any protection schemes must be lesser focused on quickly and reliably detecting and isolating ground faults. This requires special zero sequence current measurements. Next is about the protection zones and redundancy. You can think of protection as a layered safety net covering the entire power grid. We just don't protect one line, we divide the entire power system into overlapping zone of protection. Primary protection is the fastest and most selective. It's dedicated to clearing faults in its zone. But what happens if the primary relay fails? Or more commonly, the circuit breaker it commands fails to open. That's where backup protections come in. Every single component must be covered by a secondary slower protection scheme that will operate if the primary system fails. This redundancy is non-negotiable. The zone overlap is the mechanism that ensures everything is covered by each relay C slightly past its own equipment into the adjacent bus or line. We guarantee there are no unprotected blind spots in the system. Next slide is about the core protection principles. So the goal is to contrast the two main design philosophies, distance versus pilot. So transmissions line protect relies on two fundamental, sometimes competing approaches. One relies on the self-measurement and other relies on communication. So first is non-communication, step distance protection. This is the self-contained approach. The relay only looks at local voltage and current measurements to calculate the impedance. Because impedance is proportional to distance, the relay can tell how far away the fault is. The drawback is the time delay required for backup zones, which we will be discussing next. So the second is the communication-assisted pilot protection. This is the cooperative approach. Relays at both ends of the line talk to each other, typically using fiber optic cables. By knowing what is happening at the other end instantaneously, the relays can make an immediate definitive decision. Is the fault on our line or somewhere else? This allows for high-speed simultaneous tripping across the entire line length, solving the time delay problem of the distance relay. For the next slide, it's about the distance protections, step distance, which is the goal is to explain the distance relay operating zones and the basic formula. Distance protection is defined by its operating zones, which are based on the calculated impedance to the fault. The formula is simple. Z is equals to V over I. So let's move forward to the zone 1. This zone covers only a portion of the line. Typically 80% to 90%. It trips instantaneously because it underreaches the far end. We know with high certainty that the fault is on our line, making it high selective and fast. For the zone 2, this zone covers 100% of the line, plus a margin into adjacent bus. Because it overreaches, we must add a time delay around 0.3 seconds to allow the primary protection on the adjacent line to clear the fault first. Zone 2 provides primary protection for the far end of the line and backup for zone 1. Lastly is the zone 3. This is your remote backup. It looks even farther down the line and into the next substation. It has much longer time delay, around 1 second, and is a slow but guaranteed safety net. Last slide is about the pilot communication assisted protection. This is where protection gets its speed advantage. Pilot schemes eliminate the time delays associated with zone 2 of distance protection by using communication link. POTT, permissive overreach transfer trip. This uses a distance element that overreaches the line. If relay A sees the fault, it doesn't trip immediately. It waits for a permissive signal from relay B. If relay B also sees the fault, they both trip instantly. This uses agreement to ensure high security. Line differential protection, 87L. This is the gold standard based on Kirchhoff's current law. Simply put, a healthy line, the current going into one end must equal the current coming out of the other end. So that's all for my topic report about this. And thank you for listening.